Our paper presents a way to generate Sobol sequences of guaranteed quality projections. To produce uniform point patterns, Sobol relies on matrices and arithmetic modulo 2. For example, to compute the x-coordinate of point number 2466, one starts by decomposing this number in base 2. Then, we multiply these digits in reversed order by a Sobol matrix, and interpret the result as the binary decomposition of a real number between 0 and 1. By using S-different matrices, one obtains an S-dimensional sequence of points that can be used for Monte Carlo integration. They result in so-called T-S sequences. Here, T equals 1 means that any dyadic partition of the space in boxes of area 2 at the power T over n contains exactly 2 points per box. T is crucial for Monte Carlo integration, since low T guarantees high Monte Carlo convergence rate. To construct a Sobol matrix, one starts with an irreducible polynomial of degree e, and a small e times e initialization matrix. The most common construction then consists in progressively appending columns computed as a weighted sum of the e previous columns and a shifted column. This allows to build Sobol matrices of arbitrary size. In the block construction of Faure and Lemieux, they instead build matrices by blocks of size e times e, taking a combination of a block on the left of the current block, and on the top left, each multiplied by some matrices q and f. We found that Sobol matrices for polynomial p and p squared are the same, if and only if they match on the top left 2e by 2e block. Further, the corresponding matrices q and f are merely related by a tensor product with an identity matrix. This forms the basis of our new recursive construction of Sobol matrices that double their size at each iteration by squaring polynomials. The characteristic matrix of a 2D Sobol sequence, introduced by Ahmed and colleagues, consists of one Sobol matrix times the inverse of the other. It uniquely characterizes a 2D Sobol sequence up to a permutation of sample indices. We found that the characteristic matrix can also be constructed recursively in a similar way. Importantly, we show that when using pairs of polynomials of the form p and p squared plus p plus 1, the characteristic matrix has the peculiar form of the following recursion, exhibiting self-similarities. Ahmed and colleagues found that when all square submatrices anchored at the top row of the characteristic matrix have non-zero determinant modulo 2, then the 2D sequence has t equals 0. Unfortunately, regarding Sobol sequences, and up to a permutation of indices, there is only a single pair of polynomials with t equals 0. Instead, we show that when all rectangular submatrices of size W1 by W are rank deficient by at most 1, the resulting 2D sequence has t equals 1. Finally, we show by induction that, under the following conditions on the first iteration of our recursive characteristic matrix construction for polynomials p and p squared plus p plus 1, the resulting sequence has t equals 1. We then develop an algorithm benefiting from this result that can produce many such pairs of 2D Sobol sequences. These pairs can be combined to form high-dimensional sequences that remain T-S sequences, but with t equals 1 on consecutive 2D projections. We produced 692 such dimensions.